Good afternoon. So we will start the lesson now. So the reference to the lesson is as the materials that have been discussed in the main classes by sir. So discussion on the stability is what was the topic for this week. And basically we have looked at many schemes to solve all of the problems already. I hope you can see my screen and hear me right now. Okay, so I'm assuming you can. And right. So then we have discussed all of these different schemes to resolve the governing equations numerically. And now we are trying to see whether whatever scheme that we have adopted, does that make sense for our particular solution? That is basically, is it stable? Is it going to converge? Or are we looking at a solution that cannot be achieved? Like, are we looking at a scheme that cannot achieve the solution that we need? So for that, there is this criteria known as von Neumann Stability Criteria, which you must have already gone through in the lectures. Essentially, in this case, what happens is that we begin with treating the value of the function at the n plus 1 at time level and the n at time level. Basically, because that's why we are looking at that is that because we usually write a solution in terms of the backward, forward, and the current time step. That is n minus 1, n plus 1 that you already know. So then you can represent this as a Fourier term. So then we have our amplitude term. So this amplitude term corresponds to whatever the temporal level is. So essentially, one good way to sort of visualize this is that stencil diagram. Essentially, you just take two levels. Okay. So this is the n plus 1th level and this is the nth level. So then you say that this is I minus 1, this is I plus 1, and similarly I minus 1. So basically, spatially we are moving in this straight line, and on temporally we are moving in terms of levels. So then we are basically just writing these terms in terms of like these points. We are denoting these points in terms of this Fourier term, where this is the temporal. Sorry, this is the temporal level, and this is the spatial level. So in the spatial level, how it is represented is, I'll just erase these so that I can write it again. Like it's similar to how we denote our complex numbers. Okay, so then we have a theta and we have an iota. So over here, iota, this I that we see over here, just as in the lectures, we are not denoting this I is the spatial location. This is not the iota. Okay, location. This is the iota, and this is the phase angle theta. Okay, essentially what we did is that we broke down our term that we have over here into a temporal as well as a spatial representative term. Okay, and by using this like denotion, stability analysis of any scheme can be done. So what our objective is to get this amplification factor, that is un plus 1 by un. So you can see this is a relation between temporal terms. Now you might be wondering why we are taking this as the amplification term, and why are we requiring it to be less than or equal to 1. So I'm sure it's already been discussed in the class, but why we are taking the ratios of the u, the temporal function, is because the error and the numerical solution both have the same decay and growth behavior. So basically, what we are essentially in words stating by using this stability criteria is we are demanding the solution to give us a smaller error at each subsequent time step. So we are telling it that my error at n plus 1 by error at n should be less than 1. That is, this should be smaller than this. That is what my requirement from the solution is. So by using this denotion, we are able to conduct the stability analysis of any scheme. And if the amplification factor is less than equal to 1 for all the phase angles, that is this k delta x this can vary, from this theta can vary from 0 to 2 pi. So we require that for each and every phase angle, the the amplification factor should be less than 1, because of what I told right now, that the error and numerical solution of the same decay and growth behavior. Okay, so I have an example over here that I have already worked out. It is similar to whatever you must have already discussed in class. And this tensor diagram is a useful tool that I typically use when I have to conduct a stability analysis. I just visualize my the points that I'm using for my analysis in terms of this tensor diagram. So then basically what I have over here, this is the normal FTCS scheme, which is an which is it an explicit or an implicit scheme? Can you type it up in the box and let me know? You have the formula right over here. Yeah, explicit. That's right. Because we are using all the known values over here. This is known, this is known, this is known, this is known. So all of your right hand side is known, and you have one unknown over here. If I had unknowns on the right hand side as well, then it would have been an implicit scheme. So how I have to work it out now is that I have to write this in terms of whatever I told earlier, un plus 1, and then let's see, where is the position. The position is at I, so then k delta x I. So I can write it like this. I can write this as un e I delta x, sorry, e I k delta x into I minus 1. So basically this is how I'm just going to open up all of these terms, and then this expression is what I get. So this corresponds to this first term, this corresponds to this other term, the second one, that is my un at the spatial location I. And then I have transposed this, I have shifted this delta to the other side. So I have my alpha delta t here. So this is basically for an, why am I getting alpha delta t over here? This is basically just the heat equation. So I'm pretty sure we all know what the heat equation is right now. I'm just going to write it down in the small thing. It is basically dt by dt is equals to alpha dt square by dt square. So this is my heat equation. So essentially I opened it up in terms of this FTCS scheme, that is center difference and forward in time. It's an explicit scheme. And then I have just opened it up in terms of the Fourier term. So when I do that, I get a long expression over here. And then what I do is that this expression I divide it by un e raised to power iota k delta xi. And when I do that, then I simplify my expression to get this what I need, g over here, and I rename this alpha delta t by delta x square is equal to some d, so diffusion factor, some random d. And then based on that, what happens is that you have your you just use your normal like I'm calling k delta x over here, k delta x as theta. So then this becomes theta on the iota, and then you use your normal how we just break a complex. This is like the polar representation of a complex number. So you use the same methodology to open it up, and this is what you get. So then you get an expression for g, which is my amplification factor. So now I need my amplification factor's magnitude to be less than or equal to 1, because of whatever mentioned earlier, because the decay or the the decay or the growth rate of the numerical solution as well as the error is the same. So then how do I go about with it? Then I say that my delta G is less than whatever this is, and then I look for the maximum value of cos theta, because I can see cos theta over here. So basically not the maximum value of cos theta, I need this to be maximized. I maximize this, like in terms of the magnitude. So I know when cos theta is equals to -1, I'm going to get a -4 over here. So this is my absolute maximum value that I could, in terms of magnitude, that I could get. And then I just go ahead and get an expression for what the D should be. Okay, so this is just like a worked out example that I've already done. Um, this you will be able to find in the Google Drive, this exact thing. And I hope it is down below heat equation. Select. Then more schemes for solving the unsteady heat equation. One is the Crank-Nicolson scheme. Again, something you must have heard in the class. So the specialty for this is that it's a explicit as well as the implicit scheme. So over here in the stencil diagram, oh, sorry, in the stencil diagram that I have over here, I'm basically using 6 data points, right? These two are related on the temporal side, therefore there's a line between them. And then the spatial terms are all being used. So then this is the implicit part because you can see n plus 1 over here, and this is the explicit part. And then once we resolve it in the similar fashion that we've done in the previous sheet, we see that this G has an expression that looks like something like this. This is something that's been covered in the classes, how to derive this. And then there's the Lassonant scheme, which is basically BTCS, backward time, central space. So then that also we just write down the scheme how we normally do, and then we go about and find the expression for G, which is this. Okay, so this is just like a brief recap of whatever has been done. Okay, so then it's important to note that these are just the two named schemes. It doesn't mean that there aren't many other schemes. You can have as many types of schemes as you want based on the number of data points that you pick to calculate your time derivative. Okay, I could pick up 5 points, I could pick up seven, and based on that, I will have a different stability response from each and every scheme. So then there are other schemes as well based on data points taken for computation. These are just the named schemes because why I have written down the Crank-Nicolson and Lassinen is because in your assignment you might see that these recurrence. Then you can directly use this expression for the G, that is the amplification factor, to solve your questions. Okay, so then the next topic that comes that you must have gone through was the multi-dimensional treatment. So in this case, basically you also what you want to do is that your I comma j or whatever your u at time level n and whatever space I j k I j or whatever. So then you want to represent that the u is varying in space as well as time. So then again, this one continues to be the temporal term, so no changes over there. But in the spatial term, since there are other independent variables now, therefore you have another expression for the angle. So you can just name this theta and this phi. And if you have another dimension, that is the z dimension, then you can have another whatever angle theta or whatever you want to call your angle. There is no problem with that. Let's call it omega. Okay. Hmm. Then basically you would have three independent variables in space, and therefore your exponential term that denotes the spatial location of the point, that becomes bigger, right? Okay, so this was just a brief recap. Now let's have a look at this first problem. Okay, so what are the governing equations for the Stokes first problem? So the Stokes first problem, also called Rayleigh's problem. Okay, and for getting the governing equation, let's write down what the basic governing equation for any flow problem is. Okay, so I'm just going to have du by dt is equal to, let's see, no, plus v du by dx plus v du by dy. So I'm just writing it this in 2 dimensions because the problem is given already in 2 dimensions, so I don't have a significant z direction. Okay, and why I said significant z direction rather than we don't have a z direction is that basically we just assume there is no variation along z, but realistically, of course, we cannot just say that a problem is 2D in reality. It's only functionally 2D because there is no meaningful variation or no meaningful flow observations that we find in the z direction. Then minus 1 by rho dou p by dou x. So this is my general governing equation. So now, for the Stokes problem, the problem definition is that essentially there is a flow between plates, and the flow is caused by the movement of the lower plate. So then, since the only the driver of the flow is the movement of the lower plate. So basically, that's the only driver. So that means there is no pressure gradient. So this term we can say is zero. Okay. Then we have u du by dx and u v du by dy. Du by dt is obviously going to be there because it's going to keep on changing with time. But for du by dx, so we are saying that there is a what do you call it? There is a fully developed flows, and then there isn't any variation in the profile as with the direction x. That is, in the this direction there is no variation in velocity. This is also a requirement. So then this goes to 0. Then v is equal to 0 everywhere. So v is 0 everywhere. So why why is v 0? V is 0 everywhere because of the no penetration condition. So V is 0 at the no for the no penetration condition at these two boundaries, and there's no variation in the V along Y. Okay. Therefore, from the no penetration condition, we have this. Okay. This you can verify by writing a similar equation for the Y momentum. So there you will be able to justify that. Let's just solve that. This is the X momentum equation. Okay. So what we get overall is du by dt is equals to this thing. Okay, so let's see which of these options are matching with that. Okay, this is telling me that, this is telling me this. Dv by dy is 0, yes it's 0, yes it's 0, this is correct over there. Du by dx is 0, yes it's 0. So then I can see that both of these A and D options are correct. So, okay, just verify is equals to 0. You can do it simply by writing the y momentum equation and having a similar treatment to that. Right. Okay. Then the next question is, for modeling the unsteady heat conduction equation through an aluminum rod of length 1 meter, Lassonine method is used. Take thermal diffusivity. Let's write down what all we already have from here. Thermal diffusivity is 97 mm square. So what does that mean? That means 97 into 10 to the power minus 6 meter square. And delta x is equals to 0.02 meter. Delta t is 0.01 meter. Okay. Oh, sorry, seconds. State whether the solution is stable or unstable. So it's asking me to calculate the G for the calculated value of the amplification factor. Assume phi is equals to pi radians. Okay, so I already have my, theta is equals to pi radians. So I'm just going to go back and refer to my formula for the G for Lassonine method. I'm just going to have a look at this. So this is also a 1D problem. So I don't need to worry about other dimensions. It's not a multi-dimensional problem because it's an aluminum rod and we're only given information regarding the heat conduction along the length. Then using this formula for G, what we have, G is 1 minus. Just keep on writing the answers in the chat box if you have already computed it. Okay, so we have to compute the D over here. So D is equals to alpha delta T by x square. So that is 97 into 10 raised to the power minus 6 into delta T is 0.01 by 0.02. Okay, so just complete this for me. Right, so then I have over here 0.00245. What I get. So 2 into 0.00425 into cos theta. So then cos theta for me over here is what? Cos pi. So cos pi is minus 1. Eventually I'll get something right. So then this is going to be like close to 1 because it's a very small value. And we can see that it's going to be around 0.99 from our options. So then we already know that this is going to be, yeah, that's the right answer, stable. So we actually didn't need to go through with calculating the G regarding this because we know, like, for understanding whether it's going to be stable or unstable, because we know that BTCS or Larsen is unconditionally stable. BTCS or Larsen scheme. So this is unconditionally stable. That's because, see, this expression for G that you have over here, this is always going to be less than 1, right? Why? Because it's like a from 0 to pi, we are always going to get like a value which is going to be a small fraction. So then unconditionally stable. This is something that's already been covered in class. Okay. So which of the following is incorrect for the Crank-Nicolson method? So can I have an answer for this? Is it is the order like order of the scheme second order in time and second order in space? Is it conditionally stable? Is it unconditionally stable? Is it an implicit method? So there are four options that I have over here. Which of these are is incorrect for Crank-Nicolson method? No, Crank-Nicolson method is is incorrect, no? So it's not unconditionally stable. Crank-Nicolson is conditionally stable. It's not unconditionally stable. I hope I'm not wrong regarding this, but according to me, this should be the wrong answer. Feel free to just say if you mean if you think that the answer should be B, then just give me a reason for that. I have a reason for why C is the wrong answer. That is why C is the C incorrect for Crank-Nicolson method, because it is conditionally stable. We have like limits for the D. Should we be? Okay, I'll check this. Why I'm saying this is that because I have over here the G, and then this should be less than 1. So this is obviously not going to be less than 1 for each case. Like it's conditionally stable. It's not unconditionally stable. So then the question is asking me to tell me what the incorrect statement regarding Crank-Nicolson method is, and the thing is that it is not unconditionally stable. So that's my reason for it. That we can even redo the analysis if at the end of the class if we have the time for this. This is not always Yeah, you were saying that, but then I'm just trying to work out whether that's true. My knowledge, it's not unconditionally stable. I'll check this out during the anyway, but that's what my um like I worked it out right now, so that's what I'm getting. Anyway, but, right. Okay, so I'll check this out, but I'm pretty sure that it should be unconditional, that it should be conditionally stable from this whatever analysis that I've done right now. Okay, we'll move on with the next question. What are the limiting diffusion numbers for von Neumann stability in 1D, 2D, and 3D unsteady heat conduction problem using FTCS? So this is the stencil for this for FTCS. So then I have 3 points in space and 1 point over in time. So now it's asking me 1D, 2D, and 3D. So for 1D, it's pretty simple. We've already gotten the like for FTCS from whatever example that I shown you in the beginning. I have my expression with G. Right. So this is my sorry expression for G in 1D. So analogously, we'll just go back and look at this example that I have over here. So then over here, like we had this spatial term for the let's say x direction or the 1D, then we'll just have to add like one more term regarding the secondary regarding the second dimension and then another according to the third dimension. So then basically I'm just going to focus on this that I have over here, this expression for G that I already copied over there. So then this is the term that corresponds to the spatial, this term corresponds to the spatial, this one. Let me just go back, sorry. So this term is the spatial term. This one I got because I had un plus 1 minus un and then I just shifted the un to the other side. So then I got this one from there. So this one is not associated with my spatial terms. So then extrapolating, I can just write down the expressions for g in 2D also. G in 2D should be d into, let's just write dx or something into, but okay. In unsteady heat conduction problem using FTCS, assume that the time step and grid size along x, y, and z directions are identical for all cases. So that is basically what they're telling me. Since D is equal to what is it? Alpha delta T by delta x square. So if delta x is equals to delta y equal to delta z, then dx is equals to dy is equal to dz equal to d. Okay, this is what I'm told. Okay, so then analogously I can write the expressions for the g in 2D and 3D. So for 2D it would be 2 cos theta minus 2. I'm just going to write t cos phi minus 2 plus d 2 cos omega minus 2 plus 1. Okay, so this is for the x dimension, y dimension, z dimension. So then for all theta, phi and omega, we are going to okay, so then the same condition will apply, that basically when my theta is equal to pi, theta, phi as well as omega, when they're equal to pi, then this coefficient of the d will be maximum. So then I'm just going to put cos theta for theta equal to phi equal to omega equal to pi. This will have maximum magnitude. So this is for 3D. Okay, this expression is for 3D. Then I have over here b into minus 2 plus d into minus 2 plus d into minus 2 plus 1. This is the modulus basically. So this is what is required of me. So essentially for the 3D expression what I'll have is that I'll have 12D. Sorry, I made a mistake in the opening the modulus. Okay, 12t plus 1 . Right. So the d, okay, minus 20, sorry, minus 20. So then basically the d should belong to 0 to 1 by 6. Okay. Right, am I right in this? Is 4 into 3 12? Yes, it is. So yeah. So basically I'm going to get the option. Let's see what is 1 by 6. So 1 by 6 is 167. So these two options are the ones that could be correct. Then similarly, if I continue the operation for the 2D one, since we already done the 2D, so that's similarly easy, analogously easy. So for 2D, sorry, G would be equal to 2 into, sorry, what was my expression? D plus theta minus 2 plus D into 2 cos phi minus 2 plus 1. Therefore, for theta equal to 5 equals to 5, maximum magnitude is achieved. G is equals to D into 2, sorry, minus 2 plus D into minus 2 plus 1. Okay, so then that means that basically what I need is minus 8D plus 1 minus into 1. Then So my requirement from the D in the 2D case is 1 by 4, which is 0.25. So here 0.25, here I need this value 0.167. And we know from our earlier investigation that for the 1D case it should be half. So then which of these is telling me this option? Option number D is my right answer for this. Right. Okay. So you see why it's supposed to be 0.167 and not 0.125. It's not an exponential sort of a variation because our expression is not exponential. It just adds. So therefore, this is my condition for stability in case of 3D FTCS. Right. Okay, so write down the maximum permissible time step in decreasing order using von Neumann stability criteria for 1D, 2D, and 3D unsteady heat equation using FTCS. So we've just done this analysis before here. See, this is like a shortened version of the analysis. If you really want to go through with the entire process, then you have to start from the expression and then divide it by UN, like how the FTCS example for 1D has been done. Right. Right. Then, okay, so from whatever analysis we've just done, where we extrapolated the expression for G in 1D to 2D and 3D, we have received that, okay, that the D, basically the diffusion factor, alpha delta T by del X square should be is what we have gotten the values for. So then if this is small, then basically since my delta x is equal to delta y equals to delta z, then basically this delta x is x square just means delta x square for all spatial lengths. Then the smaller the d is, the smaller would be my allowed time step. So then let's come back to the question. So it's asking me that which of the time steps would be the biggest. So if d allowed d permitted d, let's just see all this one. Allowed value of d is larger, time step would be larger. So which is the one in which the allowed value of d is the largest? 1D, 2D, or 3D? It's A. So in this case, A is the right answer because the D for A is 0.5, for 2D the allowed D is 0.25, and for 3D it is 0.167. Therefore, this is the right answer. Now the time step for the 1D case would be the largest. Maybe the allowed value is the largest. Okay. For unsteady heat conduction through the rod shown below in the figure, find out the temperature at node 2. Node 2. Let's mark it. Using FTCS scheme after t equals to 0.2 seconds, take alpha is equal to this, delta t equal to this, and assume initial temperature and initial needs to be 330. Right. So at t equals to 0, t1 equals to t2 equal to 3, t3 equal to t4 equal to t5 equal to 330. Okay. Now there is a gradient. Sorry, T2 equals to T3. See, yeah, so I just miswrote that. It's asking me the initial temperature of the internal nodes to be 330 Kelvin. Therefore, I cannot say T1 and T5 is also that because T1 and T5 I'm given already over here. Okay, so this is 330 Kelvin and T1 is equals to 380 Kelvin, T2 is to 330 Kelvin. So I'm asked to use the FTCS key. Okay, so FTCS. So we know what FTCS scheme is till now. So it's asking me temperature. Let's not write U, let's write temperature. Temperature at n plus 1 That is the first time step. I'm not going to write n plus 1 anymore because we know that the n over here is the 0th time step. But the location is 2 because I'm asked to find the location of 2. Delta t. So what is my delta t? My delta t is 0.2 seconds is equal to t1. It's minus, right? If this is right. What's my delta x? Delta x is 1 centimeter by 5. So then you solve for this. Okay. So once you get your, again, it's similar to the iterative process that we did the last time around. So basically using, substituting all of these values that you already know, you're going to find out this is your unknown in this case, right? You know this is known because I know it from here. Zero over here. And so then all of the other values are known. This is known. So this is known. You can see it over here. Then T11. T11 is known? No. T11 is not. Okay, T11 is not required also. Basically, T2 no. So then I just wrote in that. Okay. This I have, this I have. So it's an explicit formulation. So therefore, from the previous time step, you have all of the information already. I hope you're following. Right. So then what I have over here is, so then you can just simply compute it, substitute all the values. T21, what is T21? That is my unknown. T21, I need to find out. T20, what is T20? It's 330 Kelvin divided by 0.2. What is my alpha? Alpha given in centimeter per square, centimeter square by seconds. So therefore, my delta x can be in centimeters. Then delta x is 0.2 centimeter. Alpha is 0.4 centimeter square. So just to make it dimensionally, I had earlier taken the SI. What? Dx is dx we computed because this is 1 centimeter and it is divided into 1, 2, 3, 4. Okay, the four parts. So then it's going to be 0.25. Thank you, Tibendu. So is that okay? So I have the length. I know how many pieces it's divided into. So I know that each increment is 0.25. So from here to 0.25 to half to 0.75 to 1, right? So this is how I compute the dates, right? So what is my alpha? 0.4 into T1 naught. It is T1 naught 380. Yeah, it's 380. 2 into T2 naught 330. And what is T3 naught? T3 naught is also 330. Is that okay? So can you compute this for me? So the mean they're saying that delta t, that is, doesn't matter that it is greater than 0.25 because that matters in the case that it will not converge or something. But since our problem is asking us to find out the result using this method, so you just follow it. So you can write a comment at the end of the of your solution that yeah, since d is greater than 0.5 and that is not stable for FTCS scheme, so this is unstable. That's what you can write, but don't need to worry about one or two time steps. This is just in like basically this is also an illustratory statement in which case we can sort of understand that okay, this scheme cannot be used for this particular problem. So don't dwell too much about D when we are asked only for like two time steps or something. That's like fine. And actually delta T is 0 0.1. I have messed up. So basically what they asked us to do is that after T 0.2. So they asked us to take two time steps while meanwhile delta T is 0 0.1. Let's just compute the into 0 0.1 divided by 0.25. Okay. So it's greater than 0 0.5 as noted. So then basically it's not going to be stable, is it? Let's have a look at the stability criterion. Needs to be between 0, half to 0. Okay, no problem. But you anyway go ahead with the problem, compute the results, and then see why, like you'll get a practical feel of why this why this solution scheme is not right for your problem. Okay. Yep. Can I have an answer for the T2 one? Because then we'll have to do another iteration. I'm getting 362 for T2 one. I hope you agree. Then you repeat. Basically, what you'll need to do is that you'll need to repeat this process for T3 as well. Because you need T3 one in order to compute T3 two. Right? So for the first time step, T3 one is equal to T3 naught. That is 330 Kelvin. So why did that happen? Because for the first time step, I'm sorry, what? 239.5 is what you're getting for what? T2 one? Please recheck the answer. Because how can it drop? The the 2 is the node 2 is closer to the higher temperature node, so physically it cannot drop beyond whatever it's already is. It can only increase. If you had told me the answer for 4, that would also be wrong. Why? Because my minimum temperature in the entire domain is only 310, so it cannot go under that. Why? This is referring back to one discussion that we had earlier regarding diffusive type of equations, that essentially your boundaries are going to have, and like your boundaries cannot will be the extremes. They cannot have like a middle level value. Okay, that is the property of a diffusive kind of a problem. That if your entire you're basically growing your solution from the boundaries. So the boundaries are only higher in temperature than whatever value you have, that means that you have the wrong answer. Okay, so please recheck that. So for the first time step, T31 is equal to T3 naught. Why? Because the whatever we are using over here, whatever time steps, like sorry, whatever values we are using over here, that is T20, T30, and T40. All of these are 330 at the first time step. Okay, so then it's equal to 330. Anyway, go for the wait. Time step 1, then we go with the other time step. Right. Now I need T22. Okay, okay. Great, great, great. It's nice. Okay, so now I need, what do I need? I need T2. Okay, don't skip steps. I have a bad habit of skipping steps, but you should not do that because then that messes up with your solution. Okay, so we will, right. So this is what I have. T22 is what? T22 is what I computed, what I need to compute. This is my unknown. So I have T22 minus 362 whole by 0.1 equals to 0.2 0. Into T11. T11 is going to be constant because T, actually let me remove this now. Because these are the boundary conditions. So the boundary conditions are time invariant. This is the example of what kind of boundary condition. Is it a Neumann or is it a Dirichlet? I need an answer in the chat box. Whether this boundary condition that we have imposed, that is the temperatures at the extreme nodes, whether that's an example of a Dirichlet or a Neumann boundary condition. You can just, yeah, great, Dirichlet. Thank you. That's a Dirichlet boundary condition because we are imposing the temperature. That is, we are imposing the function at the boundary. Okay. So then T11 is equals to T10 and it's a time invariant boundary condition. Then we have 380 minus 2 into, it was 2, T21, 362 Kelvin minus T31. So what is T31? T31 was 330 as we had computed earlier. So please give me an answer for this. Just complete this calculation. Sorry, I missed. So the T2 and that I'm getting is 353.04. Is that, yeah, so then according to me it is option number C. Okay. So then as Vibhendu was mentioning earlier that this is a condition where the D is greater than 0.5, which is not conducive with the but the stability criteria analysis that we did earlier. So basically, what that let's say if we keep on continuing these iterations, we will like you can do it make a small computation program if you want to. Then you will be able to see that this is basically not going to converge. It's going to diverge because this solution is not numerically viable. So this is what we will get as a result from here. Okay. So, but for that you need to write a computer program, or you need to just if you don't want to write a computer program, then what you can do is that you can repeat these time steps again and again, and then you'll be able to get the solution, and you'll be able to appreciate where it's coming from. Okay, what is the next question? So I hope you have followed this. I'm going to move on. Is that okay? Because this is like it's mostly just like it's maths. It's nothing like special about this. But hopefully the how we go about with it is clear. One important aspect is that you have to keep on marching in the neighbors as well. Since I'm looking at the boundary condition number, sorry, the node 2, then I need to know the values for the node 3 as well as the node 1 at each of the time steps as I keep on moving on, because those are the values that I'm using in my computations. Okay, so I hope that's clear. Okay, we'll move on. What will be the temperature at node 2 after t equals to 0.2 seconds if the problem in question number 13 is solved using Larson method? So Larson method is unconditionally safe. Okay, so let's see what answer we get from here and whether that's different than whatever we got from the FTCO scheme. Okay, fine. So let us just write down the Larson schemes. Correct me if I'm wrong anywhere. Okay. So this is my expression. Let's cross check. Okay. We'll see what we have over here. So we're going to be done with the time pretty soon, but this is the last question, so we'll just complete it and then we'll finish it off. Okay. So then once again, first step. Second, delta t is 0.1 seconds, alpha is 0.4, same values as last time, delta x is 0.25. What all do I have? Just write down the list of the givens first. That is T1 not T1 equals to 380 Kelvin, T5 equals to 310 Kelvin, and T2 not equals to T3 not equals to T4 not equals to 330. Right. So then I don't know this, I don't know this, I don't know this, I don't know this. I have only information about this. This is my only known in this case. So let's see how to go about with this. Right. So then so basically now I cannot jump straight to the second pointer as such. Like I need to know this as well. So then this is going to be my in the list of my unknowns. So I'll just write things in terms of the other nodes. right? So for first step, T2. Yes, T2 not. If you have it there, 0.6, yeah, that would remain the same. The D will remain the same. And as the last problem, so the 0.6 this is the value from the last time. And this is T11, so this will be the same as last time. Not an issue. Why? Because this is once again a digital boundary condition. And this is my unknown, this is my unknown. So see, this is like a problem that is a little bit more coupled because not everything is known. Like we have two unknowns over here and we have one equation right here. So basically, we'll have to repeat this process for the entire domain in order to get the answer. We can't leave it with just 2 points like the last time now. So let's just plug in our knowns. Okay. I just erased the delta t because I've already accounted for it over here. So I'll get an equation instead of a direct answer. Getting T1 minus 330 is equals to 0.64 into 380. What is that? So this is my equation number 1. Now I'll need to write down this sort of an equation for all 5 points. This is inherently a longer step, because like longer way to do things. Why? Because we have more number of unknowns than the equations that we can get from just one substitution. So the entire system needs to be resolved in terms of equations. T31. So now one more new unknown has been added to my equation. Okay, which is this. This is a new one. This is unknown already. This is unknown. This is unknown. So I have another equation. Similarly, I'll write a similar equation for T41, and then in T41, what I get is 241 minus T40 is equals to 0.64 into T31, which is an unknown, T41 unknown, plus T51. So this is not unknown, this is a known. So here I can plug in my value. This is equal to 310 Kelvin. Okay, so basically what you're going to do is that you're going to write down all of these equations. Then you're going to have a total number of 3 equations with three unknowns, and then you can just solve that system of equations in order to get your first time step solutions. Then once you have those, you're going to repeat the process for the second time step. So we are already exceeding the time, so I'm just going to stop over here. But this is fairly easy math. But essentially, the difference between the explicit and the implicit method is that in the explicit method, you could just simply plug in the known values and you were done. You were able to calculate your the temperature at the node that you needed. Okay, you just needed the equation for that node and plus the neighboring one. So that's about it. But here you will have to like go through the entire domain before you even start to get a solution. So you're going to get a system of equations rather than any particular value. So I'm going to conclude the class for now. Just this one last question that was also there, that pick the correct choices from the following statements made regarding explicit and implicit discretization schemes. Explicit schemes are less stable than implicit schemes. Explicit schemes and implicit schemes are both stable. Explicit schemes are unconditionally stable, or explicit schemes are conditionally stable. So you know the answer for this already, and I'm just going to leave it to you. But just in case you do not know the answer to that, then it is basically this. This is the correction. Less stable. Explicit schemes are less stable than implicit schemes, and explicit schemes are conditionally stable. So these are the two correct answers for this. Okay. So I'm going to end this class now. I'll just work out the solution and I'm going to upload it onto the Google Drive and you can just go and refer to that over there. Okay, then thank you. I hope this was of some help. Right. Okay, thank you. I'm here for another few minutes if you have any particular questions.